The point is that light load and these loads are overestimated or not estimated correctly. So unreliable. We never know what's the real light load in any building. But we assume something and then we multiply it by some factor. And wind load, we have no idea. Earthquake, completely no idea. Right? We don't know what earthquake will come here in 100 years or 500 years. Right? How can we design for an earthquake that we don't know? Of course, we will talk about. Dr. Penning will, of course, will deal with that next time. So, in any case, estimating the load is a big problem. Estimating the capacity is less of a problem now. Estimating the capacity we can now estimate better, and that's this course is about estimating capacity. So we are going to concentrate on this side of the equation, strength. Action will be next course. These are the structures that you can handle or you are supposed to handle when you go to the structural design office. So this knowledge should be sufficient to do that. So let's look at the structural design process. Structural design is the process of proportioning the structure to safely resist applied forces in the most cost-effective and friendly manner. This is kind of my definition of structural design. So if you look at this definition, it has too many things in it. Very simple sentence, but many problems there. First of all, proportioning the structure. What does it mean, proportioning the structure? If you look at each word, you will find a deeper meaning. Proportioning the structure. Not only dimensioning, but putting the members. How many columns I will need in this room? Where to place them? So it's not just proportioning, it's also placing the members in the right way. Should I use 5 meter grade or 10 meter grade or 7 meter grade? Should I use steel structure or concrete? So the whole concept of developing the structural system comes under the proportioning. Type, spacing, size, direction, type, so many things. So structural proportioning is a very complicated task. You need expertise, you need experience to see what am I going to do with this structure. Am I going to use a frame structure here, or am I going to use a shear wall structure here? Am I going to flat slab or beam slab? These questions are never ending. What system should we use? Right? And that part is called proportioning. And then finding the sizes, estimating the dimensions to start with, and then finalizing the sizes. So this is actually your major task is going to be on proportioning of the structures. Selecting the materials, selecting the material type, selecting the material strength, selecting the column sizes, selecting the reinforcement amount, selecting the pattern of reinforcement. How many bars I will put here? This way or that way? Which diameter? Am I going to put stirrups or not? So your questions are never ending, which all are related to proportioning. And then why? To safely resist the applied forces, because we want safety. We don't want it falling down. People rely on us for safety, right? Engineered buildings are supposed to not fall down, so they must be safe. So if they are supposed to be safe, then we need to make sure that we are able to calculate the capacity and the action and apply that equation. So first you proportion, then you estimate the load, then you estimate the action, then you calculate capacity, then you compare them and make sure that your structure is safe. Most cost-effective manner. You cannot make something which is very expensive. Nobody will want it, right? It must be cost-effective. It must not be so expensive that nobody wants it. Making it safe and too expensive, not good. You have to make it practical. You have to make it cost-effective. You must make it in a reasonable cost so people can construct it. And friendly manner. What is friendly? Yes, environment friendly, comfort friendly, architectural conformance. Many meanings of this friendly will come in, right? So it's not just that and it should be aesthetically looking good also. So it should be friendly for construction, friendly for living, friendly for environment, friendly for eyes, everything, right? Friendly for maintenance, friendly for decommissioning, friendly for operation. So everything, it should be friendly. You should not make something that cannot be used effectively. So this is the definition of structural design. So when you do that, you must take care of everything. But most of the time, engineers only worry about safety. They don't think about anything else. So they come up with structures which are very expensive, or they look very ugly, or nobody likes them, or they have too many columns, or they have too many big things, because they are only thinking about safety because that's what they are taught. But structure is more than that. Structure is part of a system, which is, as I showed you before, it's doing some function. So it must do that function properly, must not interfere with the function. So please remember this definition when you become a structural engineer. You are a structural engineer, right? You already graduated. So basically what we're saying is, we have load effects. Please, each word that I write has a very clear meaning. I did not choose the words randomly. Here I'm using the word load effects, not loads. We do not design the structures for loads. If somebody tells you that person doesn't know structural engineering. We design the structures for load effects, the effects produced by the loads. So we do not design for live load or dead load. We design for bending moment produced by live load, or stresses produced by live load, or stresses produced by dead load. So we do not design for load. We design for the effect. We do not design for temperature. We design for the effect produced by temperature on a structure. Two different things, not the same. So we take the load effects, we take the requirements from the client, from the architects, for building officials, and some constraints. Something you can do, something you cannot do. That is the most difficult part. Architects mostly will tell you, oh, you cannot have a beam here. So you have to design within that constraint, no beam. Or I cannot put a column here, or the column must not be bigger than this size. Then that's a constraint. And you must learn to design that. A lot of engineers fight with the architects. They say, oh, no, I cannot do this because it doesn't follow in the code. And that, what happens? The architects fire the engineer and they find another one who can do that. So never say no to an architect or a client. If they want something, say, yes, I can do it. Just give me whatever you want. Right? So never say no. Yes, we can do it. And then find a way to do it. And this design process is finding a way to do it. In this process, you find a way to satisfy load effects, requirements, and constraints, put them together, go through the design process, and come out with material specifications, cross-section details, member sizes, and configuration, proportioning, which is everything. So you first say, okay, if somebody says, I want to carry, I want to have only one column which should support 100-story building. You say, okay, sure, why not? I will design it for you. Give me a concrete which has a strength of 1,000,000 psi. If they cannot give them, you say, okay, not my fault. I designed this column for concrete with 1,000,000 psi. You cannot give me that. Not my problem. Bring me a material which has that properties, right? So that my point is that you can always specify a material needed for something. If they cannot produce this, it's their fault, not yours, right? It's cross-section details. Same is the case. Many times we get into a situation when the column size is restricted, we say, okay, we want to make it in steel and fill it with concrete, and then fill it with bars, and fill it with whatever. And if they really want it, they do it. If they say, oh, it's not, then we say, okay, make it bigger. So my point is that you should always have a solution for a problem. Then member sizes and configuration, how to arrange it. So this is the overall design, structural design process. Everything is within this slide, right? Anything that you think is not covered here, please tell me. Good. So normally this whole thing, design, is carried out in these steps: conception, modeling, analysis, design, detailing, drafting, costing. That is the logical way we go. Conception means you make a concept, how you're going to do these things, the system development. Then you model it. Modeling means, as I told you yesterday, or on Wednesday, you forgot already, structure is too complicated, you need to create a model around that, simplify it. So model is a simplified representation of the structure. You represent the structure, your concept and model, then you do the analysis. You take a computer program, you put this model inside, you run it, you get the response. Then you design it. Remember designing, reinforcement, sizes, all of that. Detailing, how the reinforcement will be laid. 2 layers, 3 layers, spacing. What is the bend? What is the splice slab? Things like that. How it will be constructed. Drafting. Then somebody has to make a drawing. You know, in America, in most places, the salary of a structural engineer and a draftsman is the same. So companies use the structural engineers to make the drawings also. So structural engineers are almost, a lot of the companies, they employ structural engineers to make the drawings because draft person and engineer have the same salary. So it's much better for the engineers to do that than having it. So you also, people have to learn drafting or detailing also in many countries. And then costing. Finally, you also have to do costing. But the problem is, this step-by-step thing never works in real world. Because the client comes in and he says, okay, I have a building I want to make here. What is the cost of that building going to be? And if you tell him, please allow me to do the concept and then modeling and design, and then by that time he has already left your office. Because he doesn't want to hear that. He wants to get the estimate, things like that. So we need to learn a concept of integrated design, in which design can start at